So K-means has been shown on artificial generate dataset that the performance can be arbitrarily bad because one of the factors is the centroid is computed in such a way that outliers could actually highly impact that. And this centroid can be actually, it's an artificial point. There's no data point actually represented by the centroid. So PAM is a method developed to address such issues. So PAM is better tolerant of outliers. The basic ideas are very similar to K-means, except that the central point is actually a real data point. The most representative data point for a cluster, we call it Medoids. The book description of the PAM algorithm is slightly different from the original PAM description. So I added a link here so you can see that. We will use this cost function shortly, but let me explain this. So now imagine that we have some Medoids has been selected. So those are the central points. See, we have a data set that we want to create 3 clusters. So we have 3 Medoids. So K is 3. So number of clusters is K. So for each clusters, what we do is to compute any point in this cluster to the central point, Medoids. And we sum up this distance, each of the distance of the points to its Medoids for every cluster. So this is our arrow function, also called cost. Okay, so later when we look at the algorithm, we're going to use this cost function. The idea is obviously to reduce the cost. So in the original description, the PAM algorithm have 2 steps. One is build, another is to swamp. So the build step in the original paper, gave you a mechanism to select the initial K-Medoids. In our book, this step has been reduced to just randomly select a K initial Medoids. As we know that initial K can make a difference in partitioning clustering. So this selecting this initial K might actually works better in reality. So the first Medoid is the data point that is at the center of the data set. We can compute the distance of all the data points to the other data points to find which data point is actually in the center. Then with this Medoid selected, a subsequent Medoid is selected to decrease the sum. So the sum of the error over all objects of the dissimilarity, the distance, to the most similar selected objects. This long sentence is awkward to read. But what it says is we have the first Medoid selected, then the second Medoid, we need to find such a data point. Okay, I should explain it this way. So we have the first Medoid selected, and we select the second, select any data points as the second Medoids. Then we divided all the data points to those 2 Medoids. The points that's closer to these 2 Medoids are assigned to those 2 Medoids. So then we compute the distance between our data points to those 2 Medoids. So then we have a total sum of error, right? Then we try all the other data points as Medoids candidates and find the Medoids that actually give us the smallest error. So that's going to be our second Medoid selected. So now we have two Medoids, and then we select the third one using the same mechanism. So this way we can select the initial K-Medoids. But the Medoids selected this way is not oh, I'm sorry, this dog. So the build step give us a very rough clustering already, and the swamp step going to refine the clusters. So the idea is to replace Medoids to improve quality. So quality again is defined using the arrow function that we discussed earlier. The idea is to iterate the following steps until there's no quality improvement. So we're not reducing the arrow further by swapping points. Consider all pairs of I and H. I is a Medoid, H is other data points. If we replacing I with H, will that give us smaller arrow? And we will compute this arrow and find the pair, the swamping that actually give us the greatest error reduction. So graphically, we can use this example to illustrate the idea and also show you why PAM is highly computationally costly. It's very expensive. So let's say we have those data points and we want to create two clusters. So first of all, we can either arbitrarily choose or randomly choose K objects as the initial Medoids, or we use the mechanism described in the build step to select this two initial Medoids. Then we assign each remaining objects to the nearest Medoid. So we can see those 3 points are closer to this Medoid, and those 5 data points are closer to this Medoid. So we roughly have these two clusters. But these two clusters may not be the best cluster, right? So we will start the swamp process. So the idea is to swamp every pair of I and H that we can find in this data set. So you can see we can consider swamping this with this points, or swamping this with that points, swamping this with that points, swamping this with that points. So we compare exhaustively all possible pairs of I and H, so Medoids and the non-Medoids data points, and try to find the best error reduction swamping. Okay, so we will just use one example to illustrate the swamping process. So initially, before swamping, we compute the cost. The cost is 20. The cost is computed using our arrow function here. So what we did is to compute the distance to compute the sum of the distance from the data points to the Medoids for each of the clusters. Okay, so in this case, we use Manhattan distance. It's easy for you to see. So here from this point to this point, we have a distance of 2. This point to this point, we have distance of 3. And by adding, so you compute the total distance in this cluster, and add that to the total distance that you found within this cluster. That gives us a total cost of 20. So now if we consider swamping this point, this data point with this Medoid, and now this becomes the new Medoids. Okay, so now we have these two Medoids. After this swamping, then we compute the distance again. So now the distance, again, we assign those data points to the closest data points. We're probably going to still have the similar assignments. So all the data points close to those two K-Medoids will be considered a cluster. And now we compute the distance of the points to its cluster, to its Medoids. So here we have a distance of 2, and this point we have a distance of 3, and this point we have a distance of what, 5? Right, so that's 2 and that's 3. So so we compute this cluster and then we add the distance, the sum of the distance to the sum of the distance of this cluster. We find out that our total cost now is actually 26. So 26 is greater than 20, therefore this swamp cannot be chosen. So we give up on this data point. We see this swamp is not successful, and let's try swamp this centroid with this green data point and see if that's going to improve the cost. So we do that exhaustively. So we're going to actually, after this try, we could actually try to swamp this data points with that with this Medoids. After this exhaustively many times, you can see this is a nested loop. That's where the computational cost come from. And for each swamp step to decide to change to swamp, to make one change, swamp this data points with this Medoids, we do an exhaustive set of comparison. And then we might need to swamp this new found that Medoids to another point that could actually further reduce the cost. So then we do this exhaustive test again. So therefore, PAM is a very costly program. Anyway, so we repeat this many times until there is no cost reduction. In this case, we're probably going to, in this example, we might actually find this is a good candidate to replace this Medoids. And then we further continue to try, maybe this should be replaced with this, or this should be replaced with this. Okay, so I think you get the idea. Okay, so as you can tell, the strength of PAM is, well, first of all, any data points that have a distance function defined can actually use PAM. For k-means, we can't. We have to use the attributes that you have must have a mean defined. So it has to be numerical attributes to use k-means. But for PAM, you can use any combined mixed data type. Remember, we have studied how to compute distance with mixed type, with binary, with ordinal data, with numerical data. So PAM have broader application. Another good feature, I think, most also for explainability, right? Because the centroids of clustering produced by PAM is actually the representative examples for a cluster. So you can ask the algorithm to actually produce output the representative examples that represents every cluster. In practice, it's very useful, and k-means cannot provide you with that. You have to do really complex summary functions. But the drawback is k-means is very highly costly. So it works only effectively for small data set. It does not scale well for a large data set. It works with any data type with a distance measure defined. So in our exercise, you're going to see that we're going to use a distance function on Gao to compute mixed type distance. The algorithm to compute Gao distance is actually very similar to what we have discussed before, the weighted sum of different types of different attributes one by one with a weighted sum. So how to improve PAM? We can actually use sampling method. So Clara is a method to perform PAM on samples. And clearance is another further improvements of Claran that randomize resampling to improve the effectiveness of samples.